People very often ask me both how and why I started my podcasting journey. Well, as an engineer, I'm frankly very passionate about math. I wanted to find somewhere to share stories of great mathematicians from Archimedes to Alan Turing and everyone in between. And for that reason, I want to tell you a little bit about my preferred hosting platform, which is Zencaster. Now, before I continue, this is usually the conversation I have with anybody who is wanting to start their own podcast. I know there are so many people out there with passions that they want to share with the world or unique knowledge that they're just looking for a platform to start with. And Zencaster is a wonderful all-in-one platform. What I mean by that is you can do your recording and your editing and use AI to create a transcript and distribute to all platforms, including Apple Podcasts or Spotify or anywhere else where podcasts are played. For anybody like me who might worry at first about what you might sound like on an audio recording, Zencaster's post-production process makes you sound really, really smooth. It automatically removes any of the ums or ahs in your recording. It removes any of the awkward pauses in conversations, and it also helps you to set the right podcast loudness and levels while reducing any background noise, all with the click of a button. It couldn't be easier. Go to zencastr.com/pricing and use my code BREAKINGMATH, and you'll get 30% off your first month in any Zencaster paid plan. I want you to have the same easy experience I do for all my podcasting and content needs. It's time to share your story. Fairly often, I get asked questions about how I got started podcasting with the Breaking Math podcast, and I'll often be asked this question by those who are thinking of starting their own podcast. That is, people who are looking to tell a story or share their unique wisdom with a larger audience or their passions, or maybe just advertise their business or services. I usually like to start this conversation by either showing off or telling about our preferred podcasting platform, Zencaster. Zencaster is essentially an all-in-one podcast hosting platform. On this platform, you can do everything from recording your episodes to editing your audio and video files to distributing your podcast to all podcasting platforms, including Apple Podcasts, Spotify, iHeartRadio, and wherever else podcasts are played. Now, there's more. When I first began podcasting, I used to get very nervous about how I would sound. I would sometimes stutter or have awkward pauses or other audio blemishes in my recordings. Now, Zencaster has a new suite of AI tools in their post-production process that make you sound really smooth. They automatically take out any of the ums or ahs in your recording. Also, they automatically take out any of the awkward pauses in your discussions. The tools will also help you set the right loudness and balance all the levels while reducing any background noise, all with the click of a button. Doesn't sound too bad, does it? You really should check it out. Really, the world needs to hear what you have to say. In fact, I'm going to give you a code below to help give you a large discount. It's all one word, Breaking Math. Go to zencastr.com/pricing and use my code BREAKINGMATH, and you'll get 30% off of your first month in any Zencaster paid plan. I want you to have the same easy experience I do for all my podcasting content needs. It's time to share your...
Mathematics, like any intellectual pursuit, is a constantly evolving field. And like any evolving field, there are both new beginnings and sudden unexpected twists, and things take on both new forms and new responsibilities. Today on the show, we're going to cover a few mathematical topics whose nature have changed over the centuries. So what does it mean for math to be extinct? How does this happen? And will it continue forever? All this and more on this episode of Breaking Math, episode 44, Vestigial Math. I'm Sophia.
And I'm Gabriel.
And you're listening to Breaking Math. First, we got some plugs. If you want to support the show, you can support us on patreon.com/breakingmath. We're putting up ad-free versions of the episodes for the $5 tier or more, and also the outlines for the show. And if you donate pi to the $E every month, which is $22.46, you can get our poster.
Yeah, that's right. We're also selling our poster on our Facebook as well. That's facebook.com/breakingmathpodcast. You'll also see a lot of Sophia's phenomenal Photoshop work. We do a lot of mathematical memes that we take great pride in. There's a lot of humorous stuff up there, as well as some great pictures, and there's some visual stuff that you just can't get on a podcast.
Yeah, and you can buy the poster there too for $22.46, and we got the shipping and handling down to $6.25. So if you're looking for a holiday gift for someone who likes Einstein or likes vector calculus or just like vector analysis at all, or just likes having kind of a fancy poster, I'd suggest buying that.
Yeah, the poster looks great on anyone's wall, especially those who like math and physics. It's just a great piece to have and a great conversation piece.
Oh yeah, and of course we have if you want to look at more visuals, like interactive visuals, you could go to breakingmathpodcast.com, and you could contact us at Twitter at breakingmathpod and breakingmathpodcast@gmail.com. You can send us your inquiries, favorite problems, because we started doing the problem episodes, and we might put some inquiries on there. We haven't really decided what to do with those, so we'd like your feedback.
Yeah, actually, I'll even second that. If you have a favorite math problem of all time or a couple of favorites, please send them. We'd love to read them. We'll email back to you, and as Sophie alluded to, perhaps we'll do a problems episode on them if it's a good fit. I think that would be a really cool idea, but we'd love to hear from you for sure.
It's kind of weird that math can seem to go extinct.
Yeah. And do you mean math or I suppose forms of math or subsets of math?
Yeah, I mean like mathematical techniques. And the reason why we're calling this vestigial math instead of extinct math is because, like a whale, for example, they still have hip bones and they still use them for mating, but they don't, support their weight anymore. So like, all of these things, they're still valid math. It's not like the math doesn't work anymore, but it's just we have better tools for certain things. It's kind of like Roman numerals. That's a really simple example of a notational system that's not used anymore.
Yeah, absolutely.
This is used sometimes in movies and stuff, but sorry.
Oh no, it's all good. So this actually, this episode, this topic hits at the core of why I wanted to start this podcast in talking about math and culture, and talking about communication and human language, all of those elements. And part of that is just where you've got a method of math, of measurement or of counting, and then it has some purpose, but then it goes extinct because a better way of counting or oh gosh, how do I say this? Our understanding changes, and then our old tools are no longer useful.
Yeah, because math isn't itself a tool. I don't believe so. I believe math kind of exists in a weird pure space, but the way that we do math is filled with tools.
Mm-hmm, absolutely. As you said earlier with Romans, they didn't have a symbol for zero, so obviously that's only useful for certain things.
Oh yeah, definitely. For a lot of things, but it's just interesting how things change.
Yeah, absolutely. And one of the things we'll talk about later on is if math has been shown in the past to be incomplete with Roman numerals or a lack of irrational numbers in ancient Greece, right now, today, how is math incomplete today that we are currently unaware of? That's an open question.
Yeah, and and we know it has to exist a little bit because of Gödel's incompleteness theorem, but we'll get into all of that. The first thing we're going to talk about is Egyptian fractions. They are used in Egypt to measure fractional quantities, and they are difficult to use.
Yeah. They had a use for a while, but as we will see, very limited use, and they can't do a whole lot once you get into more advanced math. After that, we're going to get into a topic called the method of mechanical means, which was used in ancient Greece, and it's, would we say maybe a precursor to integral calculus?
Oh yeah, and it was considered so informal that it wasn't even published. It was just a letter that was found in 1906.
Yeah, this is one of my favorite forms of extinct mathematics. It's just beautiful how they thought of these ways of solving for volumes of strange shapes.
Oh yeah, volumes of strange shapes. Like parabolas and things like that. Mm-hmm. And finally, we're going to go into projective geometry, which was invented in a prison cell.
Yeah, that's a really fun one. I find that fascinating. Just like what inspires somebody in any time, whether you're in the comfort of your home or in a prison cell or somewhere else. There's just things that inspire people in all walks of life. So that's certainly a fun one to talk about.
And then the last thing we're going to talk about is what current math is going to go extinct and why and how and all that. All right, so Egyptian fractions.
So when did Egyptian fractions come about?
Well, I mean, according to Wikipedia, the Middle Kingdom period of Egypt, which was about 1700 to 2000 BC, so almost 4,000 years ago.
Isn't Wikipedia amazing? It just is. It's just one of the modern miracles.
Oh, yeah. And if you had Wikipedia at the time, maybe they wouldn't have used this system. So basically what it is it's to measure fractions. Because in ancient Egypt, mathematics, the first one was just numbers like ones, tens, hundreds, and thousands. But instead of having, it wasn't a place value system like ours today. It was, they used a symbol, like if you wanted to write 63, you'd write the symbol for 10 6 times, and then the symbol for 1 3 times.
Okay, interesting. So, why did fractions arise in ancient Egypt? What use was it?
Well, I mean, they had a complex legal system. They needed to build things like pyramids. I think agricultural planning, things like that. It was also used as a religious thing. There's this thing called the Eye of Horus, and you might have seen it before. It's the thing with the eyebrow and like the weird like curly cube below the eye, and that was used to draw fractions in the form of like binary fractions, like like part of the eye meant like 1/2. So if you part of the eye meant like a quarter, part of the eye meant 1/8, all the way to 1/64.
Oh wow, interesting.
And so that is obviously use, and the reason why is there's like a legend about the Eye of Horus, and that like the Egyptians literally had different doctors for left and right eyes. But so they had a lot of religion having to do with this, and with numbers like that, it's pretty trivial. Anything over 64, it's really easy to do that. Just 1/2, 1/4, 1/8. But if you wanted to do like, let's say 1/3, you'd have to approximate that. So they quickly came up with a reciprocal fraction system. So where you'd write down the number and you'd write like a couple of lines below it or something like that to indicate that it was a reciprocal. So you'd write 3 and then something to indicate that it's 1/3 or 1/3.
Interesting. Okay. Now, this might be a bit of a side tangent, but I'm quite curious. I had no idea that the ancient Egyptians had a doctor for each eye. What was part of their belief? Just like,
I think that the Eye of Horus is. Let me look that up real quick. Okay, so this is I found the myth that I heard about it when Set and Horus were vying for power. Set gouged out Horus's left eye. And the eye was restored, like half of it was restored, then like a quarter more was restored all the way, and I think only 1/64 of the eye was missing. Like it was a weird, it was a weird religious thing.
Oh, how strange! So you're talking about statues, is that right?
Oh no, these are just gods in their in their philosophy.
Okay, so this is a story. This is a myth.
Yeah.
Okay.
Oh yeah, no, Set and Horus are gods.
Got it. I of course should have known that. I should have known that. Okay, interesting.
Yeah, on Breaking Math, we care about two things: math and Egyptian mythology.
Yeah, exactly. So indeed, and we do not know everything, so we can be wrong from time to time. Believe it or not, either that or we intentionally put errors in our podcast for you to catch. Make sure you're paying attention.
We don't. But yeah, and it's hard to use for basic stuff because they didn't have a way of representing like 2 divided by 5. So like 2 divided by 5, they wrote that as 1/3 plus 1/15. There's no such thing as like one number over another. There's no fraction like that. Everything is just a sum of reciprocals.
Oh, wow. Interesting.
And yeah, like if you wanted to like do 2 over something, it's the general formula for that was 1 over that thing plus 1 over twice that thing plus 1 over thrice that thing plus 1 over 6 times that thing.
Wow, that gets convoluted very, very quickly. Or in other words, 2 over p equals 1 over p plus 1 over 2 times p plus 1 over 3 times p plus 1 over 6 times p. Yeah, that gets ugly very, very fast.
And it's so hard to actually add numbers in this system because like the fractions have pretty unique representations. Like 6/13, for example, in Egyptian fractions is 1/3 plus 1/8 plus 1/312.
Oh man, that would make things way too difficult.
Yeah, whereas 4/13 was 1/4 plus 1/18 plus 1 468th. There's not one number in common between those two representations.
Jeez. So did they have like Egyptian mathematicians who just made these tables of all these
Oh, yeah,
functions?
tons of tables, yeah.
Okay, I see. So basically the formula for 2 over p, if p is prime, is 2 over p is equal to 2 over p plus 1
Which reduces to 1 over something.
plus 2 over p times p plus 1.
Yeah, which also reduces to 1 over something. So, and that was just used when p is prime. I'm pretty sure, I mean, that could be used, I think whenever p is odd, honestly.
Mm-hmm. So are there things that we do now like this?
I think so. I mean, like we said, math is tools, and to think that we have the best tools, like just because we exist, is silly.
Yeah, absolutely. So nowadays there's plenty of areas of just really hairy mathematics that we don't really have a clean and elegant way of representing.
Analyzing.
Yeah, or of analyzing or representing. Like fluid dynamics is one of them.
Oh yeah, there's because fluid dynamics, it's like everything is moving and everything is moving everything. Like there are very few closed form solutions because we use it in the language of differential and integral calculus. But who knows? There might be a way of analyzing fluid dynamics that we just don't know. I mean, turbulence is something that's still very poorly understood for this reason.
Mm-hmm. Yeah, in fact, I think there was a mathematician who once said that when he dies and goes to heaven and can ask God any questions, he would ask him why quantum mechanics and why turbulence, and God will give him an answer for quantum mechanics.
That may have been Feynman.
Okay, yeah.
Don't know though.
Yeah, so turbulence is still a pretty wild field. Now, and again, it may be that we never have the tools to describe turbulence. I don't like to think that, but I mean, that very much is a possibility.
Oh yeah. I mean, it is a possibility, as we'll discuss later, because of the incompleteness theorem. But I also think in a weird way, it might be an impossibility that we'll never find any way to analyze it better. Because I mean, fluid dynamics is a very large field right now. I mean, I know that it has been like for a long time, since like the 1700s. Mm-hmm. So, I mean, we keep discovering new things in it. It's just, I guess the question is, when is the next earth-shattering discovery in terms of it?
Yeah, and I just love it because there's just no way to know that. No way at all. It's like so many people around the world are chipping away at different parts, and who knows when the next big discovery will be.
Oh yeah, math is kind of like prospecting for gold or oil or something.
Yeah, absolutely. I've read plenty of papers online, actually, of scientists who made great discoveries accidentally. Oh, that is just a great topic. Even like dark matter. I think it was a woman who was trying to search for something original, so she intentionally didn't do black holes, which is, one of my favorite topics, and she just chose some area of space to study, looking for possible anomalies, and from that she discovered dark matter. Actually, there's more to the story, but accidental discoveries are fascinating. I don't mean to go off on this tangent here in this episode, but it does relate to the question of how will mathematics as we know it now change in the future. We don't know.
Yeah, and although like now we have fractions that like are easy. Now we don't have to like have like a PhD to do 2/5, exaggeration. But like Paul Erdős, for example, who is the most prolific mathematician of all time, even more than Euler in terms of number of papers. One of his early results is he proved that there's no harmonic progression to form an Egyptian fraction representation of an integer, which means that like, all right, a harmonic progression is the opposite of an arithmetic progression. So an arithmetic progression is like 1, 2, 3, 4, or like 3, 6, 9, or like 4, 7, 10, things like that. So it's saying that 1 over an integer is never equal to 1 over like 2 plus 1 over 4 plus 1 over 6 plus 1 over 8 or anything like that. 1 over 11 plus 1 over 22, anything.
Hey, Breaking Math fans. First, I want to thank you for listening. I have an important message for everyone. You can start your own podcast right now with Anchor. Anchor lets you create and distribute your own podcast. Just get an idea, record, and upload. It's just that easy. Anyone can do it. I'm on my way to accomplishing my dream, and you can too. Just get on your device's app store and download Anchor. It contains everything you need to make a podcast. With Anchor, you can put your podcast on all the big platforms. Apple Podcast, Spotify, Google Podcast, Amazon, and more. Reach the whole world with Anchor. Best of all, Anchor is free. You have nothing to lose with a free platform. Download the Anchor app or go to anchor.fm to get started.
For our next section, we're going to talk about a topic in mathematics called the method of mechanical means. That is also a vestigial branch of mathematics that is no longer used since the dawn of integral calculus. Still, this is one of my favorite topics, and I'm really glad we get to talk about it today.
Well, even at the dawn of integral calculus, it wasn't used because it was lost to time. It was a letter written from Archimedes to Eratosthenes that delineated it, but it wasn't actually published as a regular treatise. It went actually undiscovered until 1906.
Oh my goodness! Wow, where was it discovered at that time?
I don't know. Hold on. It was discovered in the Archimedes palimpsest, which was a Byzantine Greek copy of like a bunch of Archimedes' works. And a lot of the text is erased, replaced with a religious text, which is common at the time because, like, text was, pages were so expensive. They were made out of cows.
Oh wow, I had no idea.
Yeah,
so what was it? Wait, what happened in 1906 where it turned up? Like, was somebody just was it traded somewhere and somebody recognized it and the value of it, or what?
But the biblical scholar Constantine von Tischendorf visited Constantinople in the 1840s. And he saw a little bit of Greek math on it, so he brought it home, and apparently, like, nothing really happened until 1899, where they're like, "Oh crap, this is Archimedes."
Oh wow, that would be quite the discovery. Oh my goodness.
Yeah, and then it was studied in 1906. God, things moved slowly back then.
Wow. Yeah, absolutely.
That's 60 years from discovering the artifact to it being known in the larger academic community. It took 60 years, which is insane.
Wow. Yeah. That's crazy. Isn't it wild just how academia works, and how discoveries worked?
Oh yeah, even like Euler, they were publishing his work for 80 years after he was dead or something like that.
Wow, that's crazy. Alrighty, so let's talk a little bit about what the method of mechanical means is.
Oh yeah, so it's basically used to figure out the area and volume of things.
Mm-hmm. And by things, this method would be used for like strange shapes, as we said earlier, like barrels. Is that right?
Barrels or like parabolas. I'm pretty sure that he used that to discover his formula for the sphere before proving it rigorously.
Okay. Interesting. Okay, so let's give an example of something that you can solve using this method. So basically, the basic concept of this is that you can figure out how to find the area or the volume of things, and it involves dividing a shape into infinite slices.
Which is still what we do in calculus today.
Mm-hmm.
And they call them indivisibles. And so the idea is that if you know the center of gravity of two shapes and you know that they can balance on a lever, then you know the ratio of the areas between them, or the volumes, or whatever you're finding out. So for example, like, I'm pretty sure to measure a parabola. So let's say you want to measure a parabola's area. You divide that into an infinite number of slices, and you kind of draw a triangle around it. It's a little bit, maybe we'll discuss this on the next problem episode, but you draw the triangle around it, then you cut the triangle into infinite slices, and you show that each slice in the triangle has a different unique slice in the parabola, and then they balance each other out. Basically each piece balances out, and since each piece balances out, it means that we know the ratio.
Interesting. Yeah, so I, for one, was not aware that they had concepts of infinity in ancient Greece.
Oh yeah, they not like super rigorously all the time, but like they definitely had the concept. There's Zeno's paradox. There's like Achilles and the tortoise.
That's right. So actually, I was aware. Sorry, I forgot. It happens. I guess my question right now is that, so you're starting with the parabola. How do you get the triangle that's equivalent to it? You know what I mean? Like,
oh yeah, you do kind of have to guess. It's like any other math in that sense,
okay,
and use intuition and stuff. Mm-hmm. But once you have that, you can kind of play around with it, and like you get a feel for it pretty quickly.
Mm-hmm. Now, This was used for non-rigorous mathematics. That is to say, this method of mechanical means wasn't considered a rigorous proof of anything. However, it was used to discover things, and then to prove it rigorously, something called the method of exhaustion was used.
Yeah, and exhaustion is kind of like you could prove things like that a cylinder is equal to the area of the circle times the height.
Now we say the circle. You mean a circle that is within a cylinder?
Yeah, the circle the size of the cylinder.
Okay.
And the way that you do that is that you say you circumscribe the circle with the polygon, meaning that you make a polygon where the points touch the inside of the circle, and then you do another polygon where the points where the lines touch the outside of the circle. So basically, you have one shape that's bigger than the cylinder and one shape that's smaller than the cylinder, and you show that it is not more than the upper bound and not less than the lower bound, and then you prove that the upper bound and lower bound are equal.
Equal, yeah. At which point, though?
We prove that it cannot be greater than whatever the upper and lower bound is, and it cannot be less than that.
Okay.
So since we already know that with the polygon that it's equal to the area of the cross section times the height, we could say that the inscribed polygon approaches the area of the circle, and so does the circumscribed polygon, and therefore, since it's between those two, and since those approach the area of the circle because of the idea that things that coincide are the same thing, it's a form of limits, very crude limits.
Okay, I see. Interesting. Now, what you mentioned earlier, I think just as a side fact, Archimedes had said that he wanted his proof of the sphere and the cylinder, that the cylinder is, that a sphere inscribed within a cylinder is exactly 2/3 the volume. Is that right? Okay. He thought that was his most important mathematical discovery ever, and I believe he wanted that on his tombstone, if I'm not mistaken.
Yeah, and I think they discovered his tombstone like a couple hundred years ago or something.
Interesting.
A few hundred years ago.
Should we check that real quick?
Sure. Oh, okay. Apparently it wasn't. They thought they did in the early 60s, but there's no compelling evidence.
Okay, very good.
So the last topic we're going to cover is projective geometry, which is the one that was discovered in a prison cell. So it was invented by Jean-Victor Poncelet, and he was kept as a POW during Napoleon's invasion of Russia in 1812.
Now, who was he before he was captured, and also who was he after he was captured?
All right, he was basically just someone who was in the Corps of Military Engineers. And he became a lieutenant in the French army the same year he graduated. And then he was captured, of course, in Russia. And then after, that, he published his famous work. And then and he became a professor of mechanics. So he was just kind of like a mechanical kind of person.
Okay, very good. In his work, this is a fun one. I'm not going to try to pronounce this. And I know that you and I both went to...
It was just some random text-to-speech website.
Okay. Very good. Do you want to try to pronounce this, his treatise?
Oh, yeah. I think it was Traité des propriétés projectives des figures.
And the translation of that is?
The Treatise of the Properties of Projective Figures. So basically, he was in a cell and he saw the light from his window move across the cell. And he realized that you can make math out of that. So the basic concept is that... So,
do you just see like if it was a perfect, if the alignment was perfect between the source of the light, like the sun and the window, then you would see a square that looks just like the window with prison bars, right? So basically, you'd see a bunch of rectangles. Is that right?
Oh yeah, and those rectangles would be kind of like distorted. And so, like, let's imagine you have a globe, right? And you put the globe on top of a grid, and you put it so that the point that it touches the grid is the origin at 0, 0.
Okay.
And you put a light right at the top of the globe. You can look at the parts of the globe that get projected like onto the graph paper, and that correspondence is kind of what's used in algebraic geometry. In projective geometry, because algebraic operations can be defined in these terms. For example, It's kind of like in I know it can be used for analyzing complex numbers, for example, because every point on the sphere maps to a unique complex number.
Very cool. So do you want to talk about the basic concept of this?
Oh yeah, well I mean, it's a type of geometry that can be done with just straight edges. Whitehead, who wrote the Principia Mathematica with Russell, which was an ill-fated work that was supposed to describe all of math, and then Gödel was like, nope, you can't do that. But there's three axioms in projective geometry. Every line contains at least 3 points. Every two distinct points, A and B, lie on a unique line, AB. And if the lines AB and CD intersect, then so do lines AC and BD. Basically saying that if you have two lines that intersect together and you have 2 points on each line, then you could swap out the points. So like if they're horizontal kind of lines, you can make them vertical, and that those lines will intersect as well.
Okay, interesting. Now, I have a question about projective geometry as it's used here. I'm aware of Renaissance artists who would have a lot of hidden images in their paintings. For instance, there's a painting, and I forgot what the name of it is, but there's actually a skull painted in plain view. However, it's completely distorted. There's like, oh gosh, it's almost smeared across.
It looks like a rag.
Yeah, exactly. But it's
but if you look at the painting like almost sideways,
yes,
it looks like a skull. It's pretty awesome.
So would that be an example of projective geometry?
Oh yeah, it's a type of. Describing that, you could totally describe that with projective geometry.
Cool.
Projective geometry was kind of an intermediary form of math in many ways.
Okay.
Because analytic geometry, the geometry of Euclid and people like that, very concrete kind of geometry. And then you have algebraic geometry on the other side, which is just the study of zeros. Zeros being like, if you have a certain figure, where does it intersect another one? That's kind of a zero. Just a side note, this was also discovered around the time that Galois theory was discovered by that guy who died when he was like 22, and both of them were kind of links between geometry and algebra. And basically today you use group theory for most things that you use projective geometry for, but it's not a totally dead form of math. Like, for example, the Fano plane is a type of projective plane, and it's literally so simple. It's made out of 7 points. And it can be used to describe things like matroids, which are a generalization of matrices.
So that basically wraps it up for our discussion on projective geometry. The last question in today's podcast is a bit of a self-reflective question, then it may not have any answers currently. But all this talk about branches of mathematics and aspects of mathematics that are relics and no longer used brings up the question, what current math is going to go extinct?
Yeah, I think honestly it's like I think it's kind of like saying like what's the next technology that will have a revolution, It's like we don't know. I think it's almost I think it's almost like rigorous. It is rigorous that we don't know. Gödel's incompleteness theorem states that there's no one axiomatic system for all of math.
Yep.
And so, essentially it states that. And like, that means that there's like so much stuff to discover. Like it shows that there's no monopoly on truth, really.
Yes. And also, as you mentioned, Gödel's incompleteness theorem, it proves it proves essentially that everything always has blind spots. From that, perhaps we can surmise that everything can be improved in various ways. So the possibility of things being improved, obviously is there. We just have no idea how or why. We can certainly speculate, which is what we're doing in this section.
Oh yeah, and it's kind of weird too because mathematics changed form pretty significantly around the time of Gödel. Mm-hmm. It's kind of weird that the time at which you can no longer be a master of all mathematics, mm-hmm. and the time that it was discovered that no one set of axioms could describe all the mathematics. Mm-hmm. We're around the same time. It's just kind of fun.
Yeah, absolutely.
It's a weird kind of almost cosmic thing.
Yeah. Where there will always be things left to discover, which is cool. I think that's encouraging, because if things were done, it's like, what now?
Oh yeah, right. Yeah, yeah. It's funny. I read a science fiction story where it turns out that humans were one of the only species who came up with Gödel's incompleteness theorem, because humans in this were obsessed with limits. And they talked about in the story how aliens had a different form of relativity that didn't rely on limitations. And like, and that gets into the idea, like, there's also kind of like the idea of like diversity that exists within mathematics now. I think it's almost impossible to not have diversity, because if you can't know all of math, then you're always going to be able to discover new techniques. And those techniques, like, you take any two ideas and mash them together, you get a new idea.
Mm-hmm. One of the things that we'd mentioned earlier in this episode is we talked about how Egyptian fractions got real hairy real fast, and there's just certain things that were very, very difficult to do. I think there are definitely areas in mathematics right now, mathematics and physics, that get very hairy very fast. Things like trying to describe turbulence, for example. So this is just like an open question. Will there be a day that we better understand turbulence? I don't know. I have no idea. As we were saying earlier, there was a mathematician, or was it a physicist, who once said...
yeah, I think it was a physicist.
Okay, perhaps Feynman or something, who talked about when he dies and goes to heaven and talks to God and asks God a couple of questions. Those questions are going to be, why quantum mechanics and why turbulence? And God will have an answer for why quantum mechanics, obviously implying that there's no answer for why turbulence. That's just a very, very difficult field.
Oh, it turns out that was Heisenberg. I mean, it is really promising. And I think that looking back on mathematics and seeing so much improvement, it almost feels less hopeless that we will discover more, because we've been doing it for, 50,000 years. I don't see any stop.
And I think one way we can end this podcast is we talk about the namesake of this podcast, breaking math. It's always being broken and reinvented. So that's we will make a prediction that trend will continue.
Oh yeah, and just like breaking news, when you discover something new, it is breaking math. Mathematics, although it is in many ways a perfect field, is also a field in which our understanding is limited by the tools we develop. We are, no doubt, going to discover things that make our current understanding of certain topics obsolete, but we won't know when that will happen until it has already happened, because mathematics is its own cutting edge. I'm Sophia.
And I'm Gabriel.
And this has been Breaking Math. Like we said, send in your questions to @BreakingMathPod on Twitter or BreakingMathPodcast@gmail.com.
Oh, and real quickly, I did want to take a quick moment and plug our last episode. It was a real fun idea. We're starting a series of problems episodes. On certain episodes, we will deep dive into a specific mathematical problem. And on our very first problems episode, which is the previous one to the one you're listening to now, we talk about calculus, specifically the chain rule, and we talk about a problem that Sophia invented or came up with. And Sophia, do you want to do a quick summary of it?
Oh yeah, but just a quick correction. That was the second problem episode. The first one was the one on piano's axioms. But it's basically saying if let's say you're walking a dog around a corner, and the dog sets the pace. What will your pace be after the dog turns the corner? It turns out that it's not constant.
Yeah, and that really blew my mind. I thought, well, of course, it'll be the same thing as the dog, but again, there's some calculus involved here. So
yeah, and we're assuming, of course, like a leash that is kept taut and not a retractable leash either.
Yes, exactly. And it's also the same problem is represented with a ladder that is being lowered down the side of a building, where it forms a triangle. The ladder is a hypotenuse of a triangle, and it's being lowered at a constant rate. Right, like it's...
like it's sliding down the wall at a constant... It's sliding down the wall such that the point that it touches on the wall is moving down at a constant rate.
Yes, but that doesn't mean that the legs touching the ground are necessarily going at the same rate as the part that is touching the wall.
Yeah, and you could kind of think about this intuitively. If you have a ladder that's almost vertical, you could imagine if there's a lot of friction on the ground, pushing it down would take a lot of effort, whereas when it is almost horizontal, it takes almost no effort to move it down. So, just thank you for listening to Breaking Math, and send us your questions. And if you want to get a good holiday thing for someone, the poster is $22.46 on facebook.com/Breaking Math Podcast, $6.25 shipping and handling, United States only. And yeah, I guess, yeah.
Great way to end a podcast. I guess, yeah. We should turn that into a meme. I'm going to put a quote of Sophia saying that. That'll be your famous saying as you go down in history.
Yeah.